in many cases, it's not actually possible to evaluate the exact sum of an infinite series. So what we're going to do instead is approximate the sum. The idea is that if you look at the terms in a infinite series, since the limit of the terms needs to go to 0 as n goes to infinity, these terms keep getting smaller and smaller and smaller, closer and closer to 0. So a good approximation can be made by just including some of the first terms and dropping off the terms at the very end of the series. In other words, we can use the nth partial sum as an approximation to the exact sum. The larger the value of n that we use, the better the approximation is going to be. However, whenever you make an approximation, it's good to have some idea of how accurate your approximation is. And we will be able to quantify the error by using this inequality. So the error is also called the remainder, and it's going to be less than or equal to the integral from n to infinity of the function f of x, where this n is going to match up with the n that we use in our nth partial sum. This inequality holds as long as our function is continuous, positive, and decreasing on the interval from n to infinity. These are the same conditions that were used in the integral test. Here we will approximate the sum of this infinite series by using the fourth partial sum, and we'll also obtain an estimate of the error. So to do that, we're going to first just approximate the sum. That's the easy part of this problem actually, because we just need to sum up the terms that have this form by plugging in from I equals 1 up to I equals 4. So that gives me 4 terms. And if you add up each of these 4 terms together, you get something that's close to 0.05. Now we want to get an idea of how accurate this number actually is to the exact value of this sum. This is where we use the inequality, the the improper integral from 4 to infinity of e to the negative 3x. So, since this is a type 1 improper integral, we're going to replace the infinity by b, evaluate this definite integral, then take the limit as b goes to infinity. Evaluating this definite integral gives the quantity inside the parentheses. So it's negative 1/3 e to the negative 3b plus 1/3 e to the negative 12. Now we're going to take the limit of this as b goes to infinity. The second term is a constant, so it doesn't change, but the first term has e to the negative 3b. As you make b get larger and larger, e to the negative 3b is going to get closer and closer to 0, as this graph on the right shows. If you go far to the right, the y values get closer and closer to 0. So all we have left is 1/3 e to the negative 12. If you plug that into a calculator, it is approximately 2 times 10 to the negative 6. So that's our error, or I should say it's the maximum value that our error could have. What we have shown is that this infinite series has a sum that's approximately equal to this value, about 0.05, and the error is at most 2 times 10 to the negative 6. There's another variation on this type of problem that we'll look at here. This time we're being told what the accuracy needs to be. It needs to be 10 to the negative 12. And then we're trying to figure out how many terms do we need to include in our partial sum to get this accuracy. So maybe more symbolically, we're being told the maximum value of Rn, and we're trying to find the corresponding value of n. So we'll start with our formula that defines Rn. It is this improper integral. But now, since we have an arbitrary n here, the lower limit of integration is this arbitrary n that we'll end up solving for. Evaluating this improper integral is very similar to what we did previously, where we just happen to have a specific number at the bottom instead of n. So I won't talk through each of those steps. They're here. What you end up with is e to the negative 3n divided by 3. So that is the quantity that we need to be less than or equal to 10 to the negative 12. We need to solve this inequality for the variable n. We'll start by multiplying this 3 over to the other side. Since 3 is a positive number, I don't need to flip the inequality when I do that. Now, I see that I have my variable n and the exponent of this exponential. And to get it out of the exponent, I'm going to need to take the log of both sides. So I take the natural log of both sides. And the reason I did that is because now the left side has ln of e to some power. The natural log and the exponential function are inverse functions. And so they're going to cancel each other, and we'll just get the negative 3n on the left side. Now I would just divide by negative 3 and use a calculator to figure out the corresponding value of n. When I do that, I get that n has to be greater than or equal to 8.8. Note that when I divided by negative 3, I had to flip the inequality. You have to do that if you multiply or divide an inequality by a negative number. N, however, needs to be an integer, and so we need at least 9 terms to obtain an accuracy of 10 to the negative 12.